Hi, so now we're ready to do the last subsection of this module, and that's a subsection on integrating factors. So we've actually already seen an example of an integrating factor when we looked at linear equations. If you remember, we wrote a linear equation we could write in the form y prime plus p of x y equals q of x. And we used the integrating factor e to the integral p of x dx, and we multiplied the whole equation by it, and then that gave us a perfect derivative, and we could go on our little excursion into how to solve the linear equations. Well, now we want to find a scenario where an integrating factor can work for more general equations, and they might not be as simple as that one that we found in that case. So again, we're only going to look at some special cases because a lot of times what happens is in looking for an equation for the integrating factor, you end up with an ODE that's just as hard to solve as the original equation. Then that's not productive. So what you need is, in a few special cases, you actually get something where you can solve, find the integrating factor, and get the answer to your original problem. And those are the kind of cases we're going to stick to and look at in this course. So let's go to our trusty dot camera. Okay, and last time we looked at equations of the form m of x and y plus n of x and y prime equals 0. And if m sub y is equal to, if m sub y is equal to n sub x, then the equation is exact. Let's call it star. Then star is exact. And we can solve by the methods we learned in the last video. Okay. So what about if it's not exact? Let me give myself a little more room for writing. Okay. What about if it's not exact? Well, we're going to ask the question, can we find a function? My abbreviation for function is FCT, mu of x and y, so that if we multiply our equation up at the top by mu, can we multiply by mu and get an exact equation? Okay, so that's the question we want to ask. And if we can, such a function mu is called an integrating factor. And as I said, sometimes it's not possible to find it. Sometimes the equation to find the integrating factor is just as hard as the original equation. Okay. And so, for example, in the exact equation case, in this case, then it turns out the integrating factor is just 1, identically equal to 1. And because when you multiply by 1, you get something that's exact. Okay. All right. So it's not easy in general to solve for that. It's except to solve for an integrating factor, and except in a few special cases. So how are we going to get to those special cases? We're going to make a big suppose, and then we're going to even make some more assumptions after that. Suppose that mu isn't just some general function of x and y, but that it can be written as a function of x times a function of y. Okay. All right. And so now let's look for this equation to be exact. Let's call this one double star. for this equation to be exact, if I call this m tilde and n tilde, okay, and we're making this assumption that mu has this very special form. Okay, and now what would exactness require? For double star to be exact, we need m tilde sub y equal to n tilde sub x. Okay, so what is m tilde sub y? M tilde sub y is mu m sub y, but mu is p of x, q of y times m, and we take a partial derivative with respect to y. Well, p is when you take a partial with respect to y, p acts like a constant. So m sub y would be p q prime times m plus p q m sub y. Remember, m is still a function of two variables, so you have to take a partial with respect to that, but q is a function of one variable only, so this is really just a derivative. Okay, you only need a partial derivative when a function has more than two variables. So that is m tilde sub y. What is n tilde sub x? Mouthful to say all of this. So it is n tilde sub x. So n tilde is mu n, and now I have to take a partial derivative with respect to x. But mu is p of x times q of y, and then times n of x and y sub x. So n tilde sub x will be p prime q n plus p q n sub x. Okay. So my, m tilde y rather, equals n tilde sub x if and only if p q prime m plus p q m sub y is equal to p prime q n plus p q n sub x. Wow, that's a mess, right? So let's keep playing with that a little bit more. So let's try to get that into the form of m sub y minus n sub x. So let's bring these two things to the other side and factor out the pq. So I get pq times m sub y minus n sub x, and that will be equal to p prime q n minus p q prime m. And so m sub y minus n sub x is equal to p prime q n minus p q prime m divided by p q, which again, rewriting, m sub x minus n sub y is, okay, I'm going to write this as two terms. Notice we'll have p prime over p times n minus q prime over q times m. Okay. Okay. So if mu can have this very special form, we still get to an equation where now m sub y minus n sub x has to satisfy this with the p and the q. Well, let's see what we can do with that. Doesn't seem to be so helpful at this point. So let me set, here's the trick. Running out of letters here. Let me call it little p of x with a script is to be p prime over p of x. That's the capitals. And I'll take little q of y to be capital Q prime of Y over Q. Okay. All right, and so notice that if you solved one of these equations, for example, if you solve this equation for P, I'll leave that for you to check, that this says that capital P of X has to be e to the integral little p of x dx. That's easy to integrate, right? Just write this as d capital P dx, multiply by dx, and integrate on both sides, and then exponentiate. We've done that quite a bit so far. And q of y is, capital Q of y is e to the integral little q of y dy. Okay? Okay. Okay. So we made one assumption about our special case here, and I told you we'd make another assumption. So we're going to make two special cases. Maybe it's a good place to start a separate sheet of paper. So special case one. Let me do this for you to see these here. Q of y equals 0. That is little q of y equals 0. Okay. So, man, we don't want to have to keep track of all of that. What does that boil down to then? If you look back, if little q of y is 0, that says q, capital Q prime of a little q over capital Q is 0. So that says, this says m sub y minus n sub x is equal to m sub y minus n sub x is equal, divided by n, let me phrase it this way, is equal to P capital, that's a capital P of X. In particular, it means this quantity is independent of Y. So this special case means if you look at m sub y minus n sub x divided by n, if that is independent of Y, then e to the integral P of X, then mu of x equal to e to the integral little p of x dx is an integrating factor. Okay. Special case 2. Let me go right to the important chase for that. That's where m sub y minus, well, usually it's phrased backwards. N sub x minus m sub y divided by m is independent of x. Okay. Which is equivalent to saying little p of x is equal to 0. Okay, that's an equivalent way to say it. Okay. Then u of x, then u of y equal to e to the integral q of y dy is an integrating factor. And those are the only two special cases we're really going to be interested in. I think it would probably be better if I made this. Give me a second to do this so we can see a little more of the paper at one time when I do it. Okay. All right, let's look at an example because that theory sounds pretty darn confusing at this moment, probably to you. So let's do Get these sheets out of here. Clean piece. So let's look at two xy, that's a 2xy cubed plus 3x squared y squared plus x squared y cubed plus 1 dy dx equals 0. Okay. So m here is 2xy cubed. N is this long thing. So m sub y is 6xy squared. N sub x is 6xy squared. Well, out of ink. Hold on a second. Okay, back with a different pen. So we're taking the partial derivative of n with respect to x, so that will be 6xy squared plus 2xy cubed plus 0. And clearly it's not exact. Okay, so it's clearly not exact. Okay, so if you look at m sub y minus n sub x, that won't get you anywhere. Divided by n, that won't get you anywhere. But let's look at n sub x minus m sub y divided by m, which was another choice we had. So n sub x, that'll be 6xy squared plus 2xy cubed minus 6xy squared divided by m, which is 2xy cubed. Okay, and notice that that gives me 1. And 1 is independent. In this case, we needed it to be independent of x. Okay, so that tells us that the integrating factor if you look back in that case, that'll tell you that the integrating factor is mu is equal to e to the integral q, little q of y dy. This is the little q of y, by the way. So it's just 1 in this case. So this is e to the integral dy. So that is e to the y. Okay, so that's our integrating factor. So I multiply the equation by e to the y. So I'll get e to the y times 2xy cubed plus e to the y times 3x squared y squared plus x squared y cubed plus 1 dy dx equals 0. Okay. And now when I look, and so now this piece, where's my pen? Okay. And now this one is m tilde, and this one is n tilde. Okay. And so now when I look at m tilde sub y, so by the product rule, I will get e to the y times 2xy cubed plus 6xy squared times e to the y. Okay. And now when I look at n tilde sub x, so I will get 6x y squared e to the y, because remember you have to multiply through by that e to the y, so we have to differentiate very, very carefully. And then, but it's acting like a constant, so I can just carry it along here. And now when I differentiate this term, multiply by e to the y with respect to x, I get 2xy cubed e to the y. And notice m tilde sub y is n tilde sub x, so it's exact. So this new equation, where we've already multiplied by the integrating factor, is exact. So now we have to treat it like an exact equation. Remember how we solved the exact equation. We started by saying our first guess at psi is going to be the integral of, let's start with m tilde, it doesn't matter, dx, because m tilde is like the partial derivative of psi with respect to x on. Okay, so now that means I have to integrate with respect to x 2xy cubed e to the y plus 6x, I'm sorry, copying the wrong thing, I'm copying m tilde. I have to integrate m tilde. So that is the integral of 2xy cubed e to the y dx. So when I integrate that, the only thing that involves x is the x. So I'll get it, I get an x squared over 2, the 2's cancel. So I get an x squared x squared y cubed e to the y plus h of y, plus an arbitrary function of y. Okay, so psi of x and y is x squared y cubed e to the y plus h of y. And now I take the partial derivative with respect to y, and then I'll compare it to n tilde. So when I take a partial derivative with respect to y, I got to be careful. I get a couple of terms. So I'll get 3x squared y squared e to the y plus an x squared y cubed e to the y from differentiating e to the y plus h prime of y. And now I compare that to n tilde. And n tilde is 3x squared y squared e to the y plus x squared y cubed e to the y plus e to the y. So that tells me that h prime of y is e to the y. And so I get my function h of y by integrating the derivative of h prime, or integrating h prime rather, which is integrating e to the y dy. So that gives me e to the y, and we can put the plus c or not, we'll lump it in with the psi at the end. So our solution then, is psi of x and y equal to a constant. And what is psi? It is x squared y cubed e to the y plus h of y, which is e to the y. And now I have a plus c, but I'm just going to lump it in with that constant that's on the other side. And there is the solution of our original equation. And if you don't believe it, the good thing about ODE is you can always differentiate and check if it's true, if you got the right answer. And if you check, you'll see this is the correct answer. It satisfies this ODE that we started with in the beginning. Okay, so that's how you work with integrating factors. We're only going to do a couple of special cases because, like I said, they get pretty hard to find in general. Okay, that concludes week 2. Now get to that web assigned homework. Okay, and don't forget you have a quiz at the end of this week, which will become available on Friday morning if you've done all the modules beforehand. Okay, bye.